All right, so my project is the application of the Riemann zeta function in cryptography. So the first thing is my research question, and that's like, were there any applications in cryptography? So this is like a short thing about the Riemann zeta function in general. It's the hypothesis deals with the distribution of prime numbers on a complex plane, and it has applications in quantum field theory that are mainly undiscovered, which is why I decided to find a more practical application of it that can be sort of like used in stuff that we already have access to. Some of the relevant literature is towards the prime number theorem by Eric Cantley, and the prime number theorem proof. The literature discusses the path of logarithmic functions that show the graph of prime density, which essentially helps you understand the hypothesis better because it's based on prime density. So this is like some framework that I'm going to be using in my explanations. So one is just prime density in general, which is proportion of prime numbers within a given range of integers. So it's just like the ratio of prime numbers to the total number of integers in a range. And then the Chebyshev PSI function is a function used in number theory to approximate the distribution of prime numbers. So it basically calculates prime density. And then the prime counting function also does the same thing. The sieve of Eratosthenes is an algorithm that's used to find all the prime numbers to a specified integer. So if you're going from like 0 to 10, it will tell you like the exact amount of prime numbers up till that point. And then the RSA algorithm is a public key encryption algorithm used for secure communication and data transmission over insecure networks such as the internet, and uses prime numbers to calculate with them to make encryption codes. So I was while I was reaching the Riemann hypothesis, there's something that I had to do to like simplify it because you need understanding of complex analysis to generally approach anything to do with the Riemann hypothesis. So I had to break it down into functions associated with it and use like simpler functions to conduct my research. So I used the Chebyshev PSI function to find the applications, and then I used it to relate to the prime counting function, which is like closely related to the Riemann hypothesis. So what I had to do in order to like equivalent the two was I had to code out both of the functions, and then I had to plug in random values, or plug in random intervals to see like whether they'd give you the same results. And the results that I got were extremely similar, so I decided to just use the PSI function and the like as a replacement of the prime counting function, like while I was like coding out stuff and doing my research. And then through this, I was able to find applications in cryptography by using the PSI function and the sieve to calculate the prime density intervals, which can be plugged into like algorithms, and that would be the application. So the main algorithm that I chose is the RSA algorithm because it already uses prime numbers, and that's the easiest algorithm that I could have possibly used to do stuff that involves prime numbers. And then here's just some of the coding that I used, and this is like how I like determine equivalence because I substituted the values from like 0 to 100 for both of them, and then the return values ended up being similar. And then this is the prime counting function, and it gives you the value that's similar. So it's this and then this. And then my conclusions were that the results answered my research question because they directly showed an application of the hypothesis, and the research advances our understanding because to find new applications of the hypothesis in cryptography. And then some of the limitations are that the project doesn't like because we had to like break it down into smaller functions. It doesn't utilize every single principle of the Riemann hypothesis, but it just like combines it with established mathematical algorithms. And then some challenges that I faced were like how long specifically I'd utilize the hypothesis, and because it took me like a long time to figure out what exactly I would do with it. The applications for my work would be for cybersecurity and to use these prime numbers to enhance online security. And then here are my references.
I love it. What got you into cybersecurity?
Um, I was like doing research for with a professor, and then he basically like introduced me to it. So then I picked up this project by myself.
How difficult was the coding?
Um, because like the functions are like established mathematically, like they already have a definition. The coding wasn't that hard, but I wasn't like the most experienced coder, so it still took me time to figure out like how to code everything because you need to take like specific libraries that are already established and you need to use them together in order to like code it. So I got a little bit of help with that. It wasn't too bad though.
Oh, that's good. That's good. And is that a field that you want to go into?
Um, no, I like to have some coding experience. I'm mainly looking to become like I'm looking for like pure math.
Yeah, yeah. Um, what was the biggest challenge with the project?
With the project, it was how exactly I was going to use the Riemann hypothesis in order to code something, because like it talks about prime numbers and prime density, but like the proofs for the hypothesis aren't exactly finished, so there's no way to like you need to like sort of stress test it unless you're going to prove it yourself.
Yeah. Well, I enjoyed the screenshots. I mean, obviously you can tell that you did put in the work there, and obviously it's an important topic. So it was good to understand it. So I appreciate you
Yeah,
sharing
thank you.
this with us, Ryan. Absolutely.